Okay, so today we will discuss about some applications of direct sequence spectrum. Okay, so I will be discussing majorly 4 applications of direct sequence spread spectrum system. So the first one is this direct sequence spread spectrum signals are used in the wireless local area networks. Okay, wireless local area networks. And second application is it is used in the multiple access techniques. Okay, so one example is code division multiple access, that is CDMA. Okay, so what is CDMA and all we'll discuss in this and how this will help in CDMA. And next one is this direct sequence spread spectrum signals are used in the multipath environment. Okay? So communication over a channel with multipath, and it is also used in used for low signal detection. This one, okay, low detectability signal transmission. So these are the 4 different applications of direct sequence spread spectrum signals which we are going to discuss today. Okay, so let us take first one, that is low detectability signal transmission. So low detectability signal transmission. So here, in this case, the information bearing signal is transmitted at very low power. Okay, so that a listener trying to detect the presence of the signal will encounter a great difficulty in means the unwanted or unintended listener will find a very difficulty in detecting the presence of the signal. Okay, so let us see how and all. So that is the first application, that is as I said low detectability signal transmission. What I said here, the signal means the information bearing signal will be transmitted with low power. The unintended listener, if he is trying to detect the presence of that signal, finds a difficulty. Okay, means will not be able to detect that signal, unintended listener. Second application, as I said, it is used in multiple access radio communications. So one such example is code division multiple access. And third application is communication over channels with the multipath. Okay, so how these signals can be used in an environment where means that is in wireless, where signal travels multiple paths from transmitter to receiver, and how this system performs better than any other system. Okay, the last one is about wireless local area networks. Means how do we use these direct sequence spread spectrum signals in wireless local area networks. Okay, so let me take the first one. As I said, in this case, that is a low detectability signal transmission. As I said, the information bearing signal will be transmitted at very low power level. Okay, it will be transmitted at very low power level. That the value of low power means power level will be very small compared to the background noise. Okay, background channel noise, and as well as thermal noise, which is generated at the front end of the receiver. Okay, see, we all know the noise will be at microvolts level. Okay, it will be at the microvolts level. So we are transmitting the information bearing signal at a power level of which is relative to the channel noise and as well as thermal noise. Okay, so with that, let us see, even if I transmit a signal, means the information bears signal at that level, how only the intended user will be able to detect the signal, and how unintended listener will not be able to detect that signal. So what makes him not able to detect the signal, right? To understand that, so let me consider the bandwidth of the direct sequence spectrum signal is W hertz, and the power spectral density of the additive noise, which is denoted as N naught watts per hertz, it is. Okay, then I can write the average noise power in the bandwidth W hertz is denoted as P suffix N, that is the average noise power, so which is equal to direct sequence spectrum signal bandwidth into the power spectral density of the additive noise, that is Pn is equal to W into N naught. So these are the relations which we need to understand. Means what is the average noise power in the bandwidth of a direct sequence spectrum signal, so which is equal to what? Pn is equal to W into N naught, I said. And if I represent the average received signal power at the intended receiver is P suffix R. Okay, P suffix R is the what? Average received signal power at the intended receiver. Okay. Now, if we wish to hide the presence of the signal from receivers that are in the vicinity of the intended receiver, okay, then the signal is transmitted at a power level such that PR by PN will be much less than 1. So PR is the what? Average received signal power at the intended receiver, and PN is the what? Average noise power in the bandwidth of a direct sequence spectrum signal, right? So PR by PN will be much less than 1, means the average received signal power will be much less than the average noise power. Okay, average noise power in the bandwidth of the direct sequence spectrum signal. If we do that, then the unintended listener will not be able to detect the presence of the signal. Okay. Only the intended receiver will be able to detect the presence of a signal because of processing gain and the coding gain, which will be there with the intended receiver. Okay. So I said the intended receiver can recover the weak information bearing signal from that background noise with the aid of processing gain and the coding gain. Okay, so any other receiver means that has no knowledge of the pseudo noise code sequence is unable to take the advantage of this processing gain and the coding gain. Okay, hence the presence of the information bearing signal becomes very difficult for him to detect. So we call this means the transmitted signal. We say the transmitted signal has a low probability of being intercepted. That is LPI. Okay? Low probability of being intercepted, and it is called an LPI signal. So this is what about low detectability signal transmission. So what I said here. So in this case, what I said, the information bearing signal will be transmitted at a very low power level, that is very less compared to the background channel noise and the thermal noise. So these two will be generated at the front end of the receiver. As I said, it will be in terms of microvolts. Right? Then I assume, okay, this is what the bandwidth of the direct sequence spectrum signal, and PSD, that is power spectral density of the additive noise. I said it is N0 watts per hertz, and average noise power in the bandwidth of the direct sequence spectrum signal is denoted as Pn, which is equal to W into N0, right? And I denoted the average received signal power at the intended receiver as PR, right? Then I said that if we wish to hide the presence of the signal from the receiver that are in the vicinity of the intended receiver. Okay, means if I want to hide the presence of the signal from receivers that are in the vicinity of the intended receiver, then I need to transmit the signal at a power level of what? That PR by Pn should be much less than 1. As I said, PR is the average received signal power at the intended receiver, and Pn is the average noise power in the bandwidth of the spectrum signal. Right? When the average received signal power is less than the average noise power in the bandwidth of the direct sequence spectrum signal, then only the intended receiver will be able to detect the presence of the signal because of the coding gain and the processing gain. So processing gain is what? LC, which is equal to TB by TC. And as I said, coding gain is RC into D minimum H. There is minimum Hamming distance between the ports, right? So the receiver who do not have the knowledge of the pseudo noise sequence will not be able to take the advantage of these two. That is processing gain and the coding gain. Hence, for him it becomes very difficult to detect the information bearing signal. So we call the transmitted signal as low probability of being intercepted. Okay, that is LPI. Okay. So this is how this low detectability signal transmission happens in by using this direct sequence spectrum signal, right? So the intended receiver will be able to recover such a low power signal because he will be able to take the advantage of processing gain and the coding gain. Okay, the user means the unintended user will not have the knowledge of that pseudo noise code, so he will not be able to take the advantage of processing gain and the coding gain. Because of that, they will not be able to detect the presence of such a low power signal. Okay, so let us take one example on this. Please have a note of this problem. Okay. A direct sequence spread spectrum signal is designed so that the power ratio PR by Pn at the intended receiver is 10 power minus 2. Okay. So if the desired EV by N0 means bit energy to noise power spectral density, right, which is equal to 10 for acceptable performance. So determine the minimum value of the processing gain. So he has given the power level, okay, and he has given the value of EV by N0, and he has asked you to find out the value of the processing gain. So we can write EV by N0 as so EB means energy, right? So bit energy, which is equal, I can write received signal power into its bit duration, means power and time is the energy. So that is what I have written here. EB is equal to PR into TB, and as usual in the denominator I have written N0. That is the noise power spectral density. And then I said that the processing gain, which is denoted as LC, right, which is equal to TB by TC, right? So from that I am substituting TB as LC into TC. So that is what is written here next, right? PR into LC into TC divided by N0. Okay. Then I can say TC. TC is what? Chip duration, right? Chip interval, so which is equal to 1 by W, I said. So I am substituting that here. That's all. So PR divided by W into N0, okay, into LC. LC is a processing gain, right? Then W into N0, as I said, it is nothing but PN. That is average noise power in the bandwidth of the direct sequence spread spectrum signal. So I can replace W into N naught by Pn. So PR by Pn into LC. Right? So here all the values are given. EV by N naught is given, PR by Pn is given. So I can find out what is the value of LC. That is the processing gain. So if I substitute EV by N naught as 10 and PR by Pn, right, is 10 power minus 2, means if I rearrange the equation for LC, it becomes what? Pn by PR into EV by N naught, so which is equal to what? 100 into 10, so it becomes 1000, right? So the processing gain, I can say it is 1000. Yes, is it clear, this problem? Hello?
Yes, sir.
Is very simple. It is what he has given. He has given the value of PR by Pn, right? He has given the value of average received signal power and average noise power. At the intended receiver, he says it is 10 power minus 2, and he has given the value of EV by N naught, which is equal to 10, and he has asked you to determine the minimum value of processing gain. Means if I have a processing gain of 1000, then I will be able to detect that signal at the intended receiver. That's what the meaning is. So shall I go to the next slide? So is there any doubt?
Yes, sir.
The application, low detectability signal transmission. The thing is, PR by Pn will be much less than 1. I said what is PR and what is Pn. How the intended listener or receiver will be able to detect that such a low power signal. Why the unintended listener will not be able to detect the presence of that signal, even though he is there in the vicinity of that receiving signal. Okay, so the processing gain and the coding gain plays an important role in detecting the presence of such a low power signal, which is known to the intended receiver. Okay. So next one is, let me consider the application of wireless local area networks. Okay. How this direct sequence spread spectrum signals have been used in the wireless LAN. So you all know what is LAN, right? Local area network, and what is that is two things. Wired LAN is there and wireless LAN is there. So I hope you might have studied wired LAN in your CCN by this time, right? And wireless LAN, is it possible to give any example from your side? Wireless local area network. So you're using Wi-Fi, right? Hello?
Sir.
So wireless LAN, I think you'll be able to visualize now. So from one access point, okay, so some prescribed number of users will be able to access that device. So that is what means. Yeah, it has its own advantages. Okay, so there are two standards. Okay, there are variety of standards, but where this direct sequence spread spectrum signals are used is in IEEE 802.11 and IEEE 802.11b. Okay, these are the two wireless local area network standards, and these standards, means wireless local area networks, are operated in the 2.4 gigahertz ISM band, and this 2.4 gigahertz ISM means industrial, scientific, and medical. Okay, so this is unlicensed frequency band. In this band, we will be able to operate this wireless local area network. Okay, so what is done here is, means this 2.4 gigahertz is the bandwidth available, right? That will be subdivided into 14 overlapping 22 megahertz channels. Okay? The 2.4 gigahertz will be subdivided. That is the total bandwidth available. That is subdivided into 14 overlapping 22 megahertz channels. Okay, and out of 14 channels, all channels may not be used everywhere. So in US, they use 1 through 11 channels. Okay, let me see how this direct sequence plays an important role here. Right. So in the IEEE 802.11 standard, uh, we use a 11 chip Barker sequence. Like how do we use a pseudonoise sequence and other, in similar to that, the 11 chip Barker sequence is modulated, and it is transmitted at a chip rate of 11 megahertz. Okay, so with that the chip duration becomes 0.909 microseconds. 1 by 11 megahertz, that will give you the chip duration, so which is equal to 0.909 microseconds. So I said the 11 chip Barker sequence is used, right? So that 11 chip Barker sequence is this: 1 minus 1, then double 1, okay, uh, double 1, then minus 1, triple 1, then triple minus 1. So this is the Barker sequence used. Why this particular sequence is used is, this particular 11 chip Barker sequence has autocorrelation, which has side lobes of less than or equal to 1, compared with the peak autocorrelation value of 11. So I will come back to this, what autocorrelation and all. So now try to understand what is the Barker sequence used in this IEEE 802.11 standard, how that Barker sequence makes us to use this DS signal, right? So this Barker sequence, I said, is modulated, right? And transmitted at chip rate of 11 megahertz, right? So here the modulation can be BPSK or QPSK. The Barker sequence is modulated by using either BPSK or QPSK. So if I do BPSK, or if I use BPSK with 11 chip per bit, okay, with 11 chip per bit, then it is possible to achieve a data rate of 1 Mbps. Okay, if I use QPSK modulation, then I will be using this 11 chip per symbol, right? So here QPSK means symbol, right? So here 2 bits is 1 symbol. So with that, it is possible to achieve a data rate of 2 Mbps. Okay, means double the BPSK. This is what about IEEE 802.11 standard. And another standard I said, this is the next generation wireless local area network, that is IEEE 802.11b. Okay, so here also that 11 megahertz chip rate is maintained, but instead of using that 11 chip Barker sequence, here a set of 8 chip waveform sequences are used. What is that 8 chip waveform sequence? That 8 chip waveform sequence is known as complementary code shift keying, that we say CCK. Okay, CCK, that is complementary code shift keying is used, and we can view this CCK as a direct sequence spectrum modulation with multiple spreading sequences. So by using this, it is means by using CCK modulation in 802.11b networks, it is possible to achieve a data rate of 11 Mbps. See, there is a huge increase in the data rate, right, compared to the use of either BPSK or QPSK, which was done in the IEEE 802.11 standard. So that is the difference. Okay, in 802.11b, we use 8 chip waveform sequence, which is known as CCK, that is a complementary code shift keying, and that can be treated as a direct sequence spectrum modulation with multiple spreading sequences. So with that, it is possible to achieve a data rate of 11 Mbps. Vidhu is entering now, last 10 minutes. So last 6 minutes is left out. Don't know whether I will be able to take up the next topic. So is it clear whatever I have discussed? 2 applications. One I discussed about wireless local area network. Second one I said, first one I discussed about this one, no, detectability signal transmission. So what I said in local area network, I said 2 standards, right? One is 802.11 and another one is 802.11b. right? These are the two wireless local area network standards which will be operated in the 2.4 gigahertz ISM frequency band, right? What is done here? That total available bandwidth will be subdivided into 14 overlapping 22 megahertz channels, right? So out of 14 overlapping 22 megahertz channels, all channels are not used at all places. Only a few channels are used. In that 1 to 11, 1 through 11 channels are used in the United States, I said. So what is the sequence used in 802.11 standard is, it is a 11 chip Barker sequence that will be modulated by using either BPSK or QPSK, and it will be transmitted at a chip rate of 11 megahertz. So with a chip duration of 0.909 microseconds. As I said, the type of Barker sequence, that is 11 chip Barker sequence used is 1, -1, 11, -1, 111 and 111. Why only this particular 11 chip Barker sequence is used is because this particular sequence has an autocorrelation with the side lobes of less than or equal to 1, okay, compared with the peak autocorrelation value 11. So if I use a BPSK modulation with this 11 chip Barker sequence, it is possible to achieve a data rate of 1 Mbps, I said. Means 11 chip per bit is used, right? And if I use a QPSK modulation, it is with 11 chip per symbol, so it is possible to achieve a data rate of 2 Mbps. Okay. And in case of 802.11b, okay, here the 11 megahertz chip rate is maintained, but instead of using Barker sequence, here 8 chip waveform sequences are used. That 8 chip waveform sequence are known as complementary code shift keying. And as I said, this complementary code shift keying may be treated as or viewed as the direct sequence spectrum modulation with multiple spreading sequences. So with the use of the CCK modulation, so it is possible to achieve a data rate of 11 Mbps. So this is what about the second application, that is wireless local area network. So next one is the code that is multiple access, what I said, right? So code division, multiple access. So before I take up this application, if you have any doubts about those two, you can ask me. Hello?
Yes, sir.
If you have any difficulties about these two applications, you can ask me. Yes, 7 is there. 17. Yeah. Nandish Reddy is there. So you don't have any difficulties?
No, sir.
So it is fine with this. Okay, you do one thing. I will take up this CDMA and one more application, that is communication over a channel with multipath in the next session. Okay, so please do that homework, and those who are not taken up the quiz also can take up. Shortly, I will share another quiz and as well as another assignment. Okay.
Another assignment.
Then
already 2 is sir.
ಓದ್ಬೇಕಲ್ವೇನೋ ಈ ಟೆಸ್ಟಿಗೆ, ಈ ಟಾಪಿಕ್ ಓದೋದು ಬೇಡವಾ ಸ್ಪೆಕ್ಟ್ರಮ್ ಅಂಡ್ ಒನ್ ಮೋರ್ ಮಾಡೆಲ್
ಸ್ವಲ್ಪ ಎಲ್ಲ ಓದ್ತೀವಿ, ಸ್ವಲ್ಪ ಟೈಮ್ ಸರ್. ನಿನ್ನೆ ಇನ್ನೂ ಒಂದು ಅಸೈನ್ಮೆಂಟ್
ಕೊಟ್ಟಿದ್ದೀನಲ್ಲ ಟೈಮು. ನಾನು ಯಾವಾಗ ಹೇಳಿದ್ದು ನೀವು ಇಲ್ಲಿವರೆಗೆ ಸಬ್ಮಿಟ್ ಮಾಡಿಲ್ಲ ಅಸೈನ್ಮೆಂಟ್ ನ ಅಲ್ವಾ
ಸರ್? ಅದು ಕಮೆಂಟ್ ಸೆಕ್ಷನ್ ಅಲ್ಲಿ ಇತ್ತು, ನನಗೆ ಇವಾಗ ಗೊತ್ತಾಯ್ತು ಸರ್. ನಾನು 12 ಕ್ವಶನ್ಸ್ ಬರೀತಾ ಇದ್ದೆ.